So here's something really interesting. Even though we know that the transition between these two states is forbidden, we can excite something called the spin coherence between these two states. Here is an example of 87 rubidium atoms used in experiments, and the spin coherence is between the two spin states of an orbital. So the idea of quantum memory in our system would be to coherently map our optical field onto the spin coherence, or in an ensemble, the collective excitation of spin coherence, or the spin wave. Now, if you want to calculate the dynamics of the system like we did for the two-level atoms, we'll have to make more reasonable approximations, and we can find these using the off-diagonal terms of the density operator. And we will end up with three coupled differential equations. We also call the coherence between the ground and the excited state as polarization. Little gamma here denotes the decoherence rate of the spin wave, and d is the optical depth, and it practically describes the limit of information that we can store. Now, if the coupling of the probe field is weak, we can find steady-state solutions to these equations, and that would give us the linear susceptibility associated with the ensemble, which would guide how the probe field propagates through it. Within these approximations, there are two interesting cases to look at. The first one is electromagnetically induced transparency, and the other one is Raman interactions. So if we have a populated ground state and we shine a photon that's resonant with a transition, then it will get absorbed and we will see nothing on the other side. However, if we use this three-level atomic configuration and we have a control field that's resonant with the auxiliary and excited states, then we will obtain a superposition of these states as dress states. And now our probe field that was earlier on resonance will now pass through the atoms without being absorbed. So if we consider an ensemble in the EIT regime, the absorption and dispersion curves as a function of this two-photon detuning looks like this. So we can see that there's a single absorption feature corresponding to the transition, and within that we have this narrow transparency window where the dispersion curve sharply changes. This leads to a reduction in group velocity of the incoming pulse. This long pulse in time gets compressed inside our ensemble when this control field is on. This concept is called slow light. If we adiabatically turn off the control field, then we would have mapped our optical information and time into the spatial information of the spin wave. This being adiabatic is important because during this stage we have the formation of something called a dark state, in which there's a quantum interference between the two excitation pathways, which prevents the excitation of polarization coherence. And there's a direct mapping of the optical signal into the spin wave. Finally, when we want to recall this, again, adiabatically we turn on the control field, and all the spin wave is mapped back into the optical field, and it exits our ensemble. So this is the fundamental principle behind EIT-based quantum memories. I will give a very brief outline about this, but there's something that looks very similar to EIT, but is fundamentally different, which is the Autler-Towns splitting, or ATS. The reason it's different is that instead of having a transparency window within a single absorption peak, we have two split peaks. And there's no adiabatic control, that is, we're not preventing the excitation of polarization coherence. And there's exchange of coherence between the polarization and the spin wave. So in this case, in fact, the polarization coherence does get excited. So there's a time over which all the polarization coherence gets mapped to the spin wave, which is when we turn the control off, and to retrieve it, the reverse happens. The spin wave is converted to the polarization coherence, which excites our optical field, and we get our signal out. So far, we've discussed the cases where our control field is resonant with the auxiliary and excited states. However, something interesting happens when we go off-resonant. So when we have large one-photon detuning from the excited state, we can adiabatically eliminate the excited state, and effectively our control field will couple the ground and the auxiliary states with this two-photon resonance without an actual excited state, and it's just a virtual state. And this is what the absorption looks like in this limit, and we can see that depending on this two-photon detuning, we have a sharp absorption feature. This corresponds to the mapping of our optical field onto this long-lived atomic coherence or spin wave between the two ground states. We can control where this absorption occurs, and so an advantage of this scheme is that it does not rely on slow light, and that we can absorb different frequency components of our input pulse. To understand why this is interesting, if we have a pulse that is wide in time, it will be narrow in the frequency domain. In EIT, we have a very narrow transparency window within which we try to fit our pulse. However, if we compress the pulse in time, then it's going to be wide in the frequency domain. Thus, we're going to lose efficiency as more of the pulse lies outside the window. However, in the case of Raman memory, with the ability to control the absorption of frequency components of our optical pulse, we can create a memory system with a large bandwidth. That is, we'll have the ability to store pulses that are quite short in time. There are a lot of proposed methods on doing this, but we're going to relate back to our first video where we briefly introduced Raman gradient echo memory. Effectively in this scheme, we're changing this 2-photon detuning using an external magnetic field, which allows us to create this gradient in which each atom absorbs a different frequency component. Great, so just to acknowledge, we haven't discussed a lot of fine details like the phase relationship within a spin wave, etc., but that would be all that I want to discuss within this video. If you're curious to learn more, I've attached various references that you can go through, and thanks for watching.